Alright, so since I am not here today, I'm going to try to use some fancy new technology to help you guys still have an understanding of what you're supposed to get out of today. So what I'm going to do here is I have 3 different videos for you guys to see. It's 3 different problems, and then after that you guys will have a homework assignment to work on that the substitute teacher will tell you about. So we're going to continue along today with more graphing of polynomial functions. We'll be doing a little bit more advanced stuff today. So let's jump straight into a question here. So my question is, why did we learn how to divide polynomials? So if you think back to last week, we learned synthetic division and long division, and you should have been asking yourselves, well, like, hey, why did we do this? Okay, there's got to be some kind of point to it, and the reason is because what we're going to run into today is some problems that or some functions that we've learned a lot of different factoring strategies this year, okay, but some of the functions we see today, we're not going to be able to factor them using the methods that we've learned in the past. So whether factoring a quadratic, or factoring by grouping, or factoring a difference of perfect squares, all those different strategies that we learned, it's not going to work, and we need another way to factor. And the way that we're going to do that is by using either synthetic division or long division. So let's jump straight into a problem right here. And let's look at this function. It says, consider this function has 4 terms. Do we know how to factor this? Okay, well, in the past, when we've seen a function that has 4 terms in it, what we've always tried to do is we've tried to factor by grouping. Okay, now, but when we look at this one, you can tell right off the bat the ratio between the first 2 terms and the last 2 terms is not the same. You could try to factor by grouping. So in other words, you could take out an x squared, you have a 2x plus 5 left over. You can take out a -1, flip the signs on everything, you have a 28x plus 15. But what you'll see is we do not have the same thing in both sets of parentheses. Okay, so factoring by grouping, even though there's an even number of terms, it does not work here. Okay, now that can mean one of 2 things. Either this cannot be factored at all, or we have to use some other way, some other type of division, in order to help us factor this. Okay, so let's say I gave you a little bit more information on this function. So what if I told you that x equals -5 is an x-intercept of this function, same one we were just looking at? What can we do with this information? Okay, well, if I tell you this, we are able to factor this function. So let's do a little bit of thinking here. If x equals -5 is an x-intercept of that function, what that means is this function in its factored form, x plus 5, must be one of the factors of this function. Now, we don't know necessarily what's left over in this other set of parentheses, but we know x plus 5 must be an x-intercept, because if it is, that means when you set y equal to 0, and you have a product over here on this side, because this is the only way that we could get this x-intercept. If I set x plus 5 equal to 0 and solve for x, I would get x equals -5 as one of my x-intercepts. Okay. Now, what I don't know right now is I don't know what's left over in this other set of parentheses. Essentially, what we've done at this point is I basically told you, if you think about this in terms of numbers, let's say I told you, hey, I have the number 48, and I'm going to tell you 12 is a factor of 48. That's kind of like me telling you that x equals -5 is an x-intercept of this function. If 12 is a factor of 48, what that means is I could take the number 48 and I could divide it by 12, and when I'm done, I should get an answer that has no remainder. That's what it means for something to be a factor of another number. And in fact, when we do 48 divided by 12, we get exactly 4. Okay, now, what this means is we can now come over here and we can make a statement that says 48 is equal to 12 times 4, and 12 times 4 is going to give us exactly 48. So if we go back and think about this problem, what this means is x plus 5 times something should give us exactly this function that we started out with. Now, if we want to figure out what's left inside of this something, the only way that we're going to be able to do that is to take this original function and divide it by x plus 5. Now, fortunately for us, we can use synthetic division to make that happen. Now, I'm going to come over here and I'm going to make a little note so I don't forget what I'm doing. But I'm literally going to take this function and I'm going to divide it by x plus 5. Now if we're using synthetic division, what that means is we're going to put a negative 5 in the box right here, and then across the top we'll go 2, 5, negative 28, negative 15, and let's see what happens if we try to divide these. So I'm going to drop the 2 down, multiply, I get negative 10, add these together, I get negative 5, multiply, I get 25, add negative 3, and multiply again, I get 15. And just as we said, because x plus 5 must be a factor of this function, you get a remainder of 0 when we're done. Okay. Now, don't lose track of what you're doing here. What we've now figured out is that if I took x plus 5 and I multiplied it by this answer, I should get exactly what I started out with, and that answer is 2x squared minus 5x minus 3. And if you wanted to check this, again, if you multiply them together, you should get exactly this. Now, at this point, we don't need to use any more synthetic division, because now, if we want to factor this completely, we have a quadratic that we can factor rather easily. So what we can keep doing here is just continue to factor this completely. That x plus 5 is not going to change, but in this quadratic I'm looking for two factors of negative 6 to add up to negative 5 there, negative 6 and positive 1. So I'm going to go ahead and finish factoring this here. I'm going to take out a 2x, got an x minus 3, I'm going to take out a 1, got an x minus 3, and when I'm done I have x plus 5 times x minus 3 times 2x plus 1. Okay, this is the completely factored form of this function. So what we did is we took something that we couldn't factor at all by grouping, and by using synthetic division we were able to factor it completely. Now we are going to graph this, so let's graph this real quick. This has a multiplicity of 3. It's positive, so our end behavior, odd and positive, is going to be down and up, and we have x-intercepts at negative 5, 3, and negative 1/2, and each of these has a multiplicity of 1. So real quickly, let's graph here, and the graphing part should be pretty easy today. I'll draw in my end behavior. I'm down, up. Each one of these has a multiplicity of 1, so we'll go through, and straight through. Okay. Now, one other thing I want to note here on this is that x plus 5 was a factor, so when we divided this function by x plus 5, we got a remainder of 0. It also means, when we're done here, we see that x minus 3 is a factor, so if we divided this by x minus 3, we should also get a remainder of 0 if you want to try it. And also, 2x plus 1 is a factor, so if you divided this by 2x plus 1, you would also get a remainder of 0. And if you go back even further, if you wanted to use long division, if you took this and divided it by 2x squared minus 5x minus 3, you would also get a remainder of 0, because all of these things are factors of this function.